Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to draw good free body diagrams and apply conditions of equilibrium. So what we're looking at here, we've got this hungry bear walking along, and he looks up this cliff here and he sees this sheep eating some grass, and the bear's decided that he wants to go snack on that sheep. Coincidentally, somebody has left this 10-meter long ladder lying against the ground here. So the bear is going to climb up the ladder, and what we're going to try to calculate is the coefficient of friction. Whoops, I'm going to move that over. We're going to try to calculate the coefficient of friction required at this surface so that the ladder doesn't slide down and hurt the bear. So what I'm going to do here is start with a free body diagram as usual. But when you do your free bodies, very, very important that you define your system quite clearly. So my system is going to be this. I'm going to include the bear, right, and the ladder. So the system is going to be the bear-ladder combination. So when we draw our free bodies, we always want to clone the object and draw our picture somewhere else. I like this to be just kind of the first picture describing the problem. It's easier for me to do this with your tool. If you're doing this at home, you have to redraw it. But what I'm going to do here is copy this. All right, I'm going to move this over here for the purposes of drawing the free body. All right, so our free body of the system now. Start putting force vectors in. So the first and fairly obvious force to put in there, I'm going to put a force vector in for the weight of the bear. So that force vector is going to be down. Whoops. I like to do my force vectors in black. Equal to mg. But again, that m is mass of the bear. Now, right there, I still even have a little bit of that surface left. Actually, you don't want that in the picture, right? But we have a surface in contact right here. That's going to give us a force in our free body, and that force is going to be applied to the ladder, and that's a normal force. That force is going to be that way on that ladder. I'm going to go ahead and draw that force vector. N, and there's going to be two normals in this problem, one at the wall, one on the ground. So I'm going to put a little W here for normal at the wall. All right, clean this up a little. We don't need that there. Don't really need this. All right, another important force right there, we're going to get a normal force. And that's the force supporting the ladder. So I'm going to go ahead and put that force up. All right, that's the normal at the ground, so I'm going to tack a little G on there. Another force, we're going to have a frictional force, and that's going to be basically holding that ladder in place. Now, if we go back and kind of look at this surface, conceivably, we may have a frictional force at that surface. So I'm going to go ahead and put one there for, at least for the time being. And if that would be supporting the ladder, that would be up. That would be the frictional force, let's say, at the wall. Another force to consider may be the weight of the ladder, but I've assumed that this ladder is small, especially compared to our 400 kilogram bear here. And I've also assumed that this is a pretty darn good ladder, pretty strong ladder that this bear can climb up and get up there without bending it. But again, the bending or the effects of the material on the ladder are not an important part for this problem. So we're going to assume that this ladder stays nice and rigid. Now, when we look at this problem, we look at our free body and we start counting unknowns. We don't directly know this normal yet, and we don't know this frictional force. We don't know this normal. We don't know this frictional force either. That gives us 4 unknown forces. But we can only write 3 equations for this problem. We can write a force equation x direction, force equation y direction, and we get 1 torque equation. So right now as it sits, there are more unknowns than we can solve for. So what I'm going to do is I'm going to make an assumption here that the wall is fairly smooth at this surface. If the wall is smooth at that surface, that means that we can basically throw this one away. So I'm going to do that. All right, and here's my free body now. All right, so geometry, this 40 degrees in this picture would be right there. So now I'm going to go ahead and start writing equations. Now, there's two types of equations we can write. We can write force equations and torque equations. Torque equations are nice in that if you're clever about where you choose your point, you can typically eliminate a couple of unknowns. Right here is the point we're going to want to choose. If we choose this point right here, both the frictional force and this normal force go right through that point. So what will happen is they will not show up in that equation. We should be able to calculate that normal. So I'm going to go ahead and do that. The sum of all torques about the, I'll put lower right end, equals 0 because this thing's not accelerating. I'm going to go ahead and just keep the standard sign convention of counterclockwise positive. So the frictional force here doesn't create any torque because it goes right through that point. The normal doesn't create any torque because it doesn't go through that point, or it goes right through that point as well. So neither of these show up. And again, that was the point of choosing this point to sum torques about. Right? Gravitational force for the latter is small. We're not going to worry. So let's talk about the bear. All right. So the bear does produce torque, or the weight of the bear does produce torque about this point. But what we can't do is we can't just say weight of the bear, mg, times the length of the ladder. Because remember, torque is force times distance. Let me write this over here. So torque is force times distance. Again, that's the Greek letter tau, which a lot of books use to represent torque. But they have to make a right angle. Now, if you've seen my video on torque, there's a couple different ways you can make a right angle. You can either break the force into components, or you can break the distance into components. So what I'm going to do here is take note of this. This force vector acts all along this line. That's called the line of action for the force. The distance we need is this distance right there. That makes a right angle to the line of action. The length of this ladder is L. Now I know the bear's not, the force isn't applied right at the end. I'm just going to approximate it and say that this force vector is basically applied at the end of the beam. So the hypotenuse here would be 10 meters, or L. That makes this distance L cosine 40. So the torque term we're going to want is going to be weight of the bear, mg, times L cosine 40. I'm going to get rid of some of this stuff here before I write that out. All right. So mg for the bear times L, cosine 40 degrees. That torque term is positive because this force makes this system want to rotate counterclockwise about this point, and I've got counterclockwise positive. All right, now the normal force. The normal force acts all along this line. So the distance we need for the torque term is that distance, again, where it makes a right angle. And you'll notice that that distance is the same as this distance right here, which is opposite the 40 degrees, and again the hypotenuse is L. So the distance we need for the normal is going to be L sine 40. So we're going to have normal at the wall times L sine 40, and that torque term is negative because this force right here points to the right, and it makes this beam want to rotate clockwise about this point. Again, with torque, it's not about right, left, up, down. It's about clockwise or counterclockwise. This force is producing clockwise torque about this point, hence the minus sign. And that's pretty well it. I've got all forces considered now, so this sum equals 0. You'll notice that the length divides out, it's in each term, so the normal at the wall is equal to mass of the bear times g cosine 40 degrees over sine 40 degrees. I'm going to go ahead and calculate a number here, if you give me just a moment. Got to get my calculator up and running. Oops, where did it go? All right, so what are we going to have? I've got one of these reverse notation calculators, which I do not like, but Hopefully I can get this to work correctly. Okay, and I get 4,672 newtons. For that normal force at the wall. Right. Next step. Now we can go after this frictional force. Let's see, any room to do that. I guess I'll do that here. Actually, before I do that, if you give me a moment, I'm just going to take my entire picture here and give myself a little more room here to write. Okay, so now from our free body here, we can write this equation out. Sum of all forces x direction equals 0, calling right positive. So we're going to have plus the normal at the wall, which I know to be 4,672 newtons, minus the frictional force, and that's coming from this, equals 0. So our frictional force is 4,672 newtons as well. Now, to get the coefficient of friction, we're going to need this normal right here, because remember, the frictional force is equal to the coefficient of friction times the normal. But it's important to realize we need the correct normal. The coefficient of friction at this point is related to this normal right here. We can get that by summing forces in the y direction. Sum of all forces y direction equals 0. I'll go ahead and just do up positive, so I'm looking at my free body. We've got this force up, normal at the ground, minus the weight of the bear, so minus mg, and again that's the right, it's the bear's mass we need. And that's it. That's the only forces that showed up in the free body. So that sum equals 0. So the normal at the ground is equal to the weight of the bear. Which I get 490 newtons. 490, oh boy, let me rewrite that a little better here. 490 newtons is what I got out of that. 490. Okay. So now to get that coefficient of friction, I'm just going to use this. The frictional force, which is 4,672 newtons, is equal to the coefficient of friction times the normal at the ground. Whoops. I'm going to go back and take a look at that. That sure seems like that should be a lot more to me. Oh, I think I used the wrong. Good point here. Make sure you use the correct mass. This was mass of the bear times g. I might have looked up here and used the mass of the sheep times g. Let me run that again. So the bear was 400 kilograms times 9.8 newton per kilogram. 3920 for this normal. So my apologies for that. But again, you know, a little bit of a learning experience here. It's quite common in problems. I did actually put this here, even though it wasn't part of the problem, and I did put that there deliberately, and I ended up using it by accident later in the problem. So, you know, make sure, the lesson to be learned here, make sure that you look at where your equations came from. This equation came from a free body of this system. The bear is part of that system, the sheep is not. And that mg was for the bear, so be real careful when you take data out of problems here. So right there's the one we want, 400 kilograms. Back up here and get rid of this. I get 3920 newtons. All right, for the normal at the ground. So when we solve this for the coefficient of friction, we're going to have 4,672 divided by 3920. And we get I get 1.19 out of that, or let's just say approximately 1.2. Now the million-dollar question, you know, what does this mean, or is this correct? Well, here's what it means. Frictional coefficients typically are between 0 and 1, and they don't have to be. I mean, there are cases where frictional coefficients are higher than that. Case that I talk about in my physics class a lot of times are drag racers, right? it's going to depend on this surface here. Usually if this is a real hard surface, the frictional coefficient at this surface probably is going to be less than 1. And what that means is basically this sheep is probably safe. The frictional coefficient required to keep this thing here depends on this angle. The smaller this angle is, the less likely it is for this ladder to stay in place. Imagine this bear putting it, something like this. When that bear gets halfway up this ladder, no doubt it's going to kick up. So what this means, this is not the actual frictional coefficient here. It's the required frictional coefficient to keep this ladder in place to get the bear to the top. What does that mean as far as the lamb is concerned? It is very likely that that lamb is going to be safe today. So hopefully the bear's not, if the bear's smart enough, maybe he'll push the ladder up so that this 40-degree angle goes to 50 or 60, in which case the lamb gets eaten. But for right here, right now, a 1.2 coefficient of friction, it is unlikely that Mr. Bear is going to get to eat today. Hope this video helps demonstrate this. Have a great day.